Hi, my name is Felix Herrmann. In this episode, I hope to explain why open source and abstractions are essential for a sustainable and lower cost software solution to meet the challenges of the energy transition in the age of AI, basically making people more productive.
Welcome to Seismic Sound Off, exploring the depth and usefulness of geophysics for the scientific community and the public. I'm your host, Andrew Geary. In this episode, Felix J. Herrmann highlights the July 2023 special section in the Leading Edge, Digitalization in Energy. We start by discussing the framework for his open access article, Learned Multiphysics Inversion with Differentiable Programming and Machine Learning. Felix shares why the future of the oil and gas industry depends on the democratization of technology design. He provides insights into why modernizing wave equation inversion frameworks is important to geophysics and shares the implications for the results of his study. This episode provides a glimpse into the future capabilities of machine learning to help provide the path for the next great discoveries in geophysics. This episode is sponsored by Catalyst Data Management. Catalyst Data Management provides the only integrated end-to-end subsurface data management solution for the oil and gas industry. Over 215 employees operate in North America, Europe, Asia Pacific, and South America, dedicated to enabling digital transformation and optimizing the value of geotechnical information for exploration, production, and M&A activity. Learn more at catalystdm.com. To read July's special section, Felix's biography, and to connect with Software Underground, visit seg.org/podcast or check out the episode show notes where you're listening. Let's get to my conversation with Felix J. Herrmann. We're talking about July's Leading Edge, which focuses on digitalization in energy. What do you believe is the most tangible benefit of this move towards digitalization in exploration geophysics?
Well, I will speak a little bit from my own perspective. So I really think that developments like our differentiable programming environment, which is really a new paradigm, I think make it possible to more rapidly develop more sophisticated algorithms. In the old days of, say, complex monolithic codes, one doesn't stand a chance because you're basically faced with too much complexity. And that means there's very little room for what I call algorithmic experimentation. But now with these new environment, there is.
And you wrote a paper for July's Leading Edge. That's one of the reasons we're speaking with you here. And before looking more in depth at your paper, can you just highlight what you hope to discover with your study?
So what we try to do is to couple different types of physics and machine learning. Because if you think about, say, problems like geological carbon storage or good old reservoir engineering, you need to couple, say, the physics of fluid flow with the physics of waves. And so we're trying to do that by creating an environment that's conducive to do this rapidly, and this panned out even beyond our expectation. So, for instance, my greatest student was able to get this coupling done between fluid flow and waves up and running in a matter of days. And we found the same for trying to integrate machine learning techniques. I think it's important to remember that the goal or the end goal of building this, say, new paradigm is to create an environment that facilitates discovery and not stifle it. And that's a little bit the case with the current very large monolithic codes that the industry is still working with.
Why is a step towards modernizing wave equation inversion frameworks so important to geophysics?
Well, modernized software frameworks for, say, wave equation-based inversions allow researchers and practitioners to develop scalable, basically new algorithms. And this really accelerates innovation, something the industry and academia desperately need when we want to, say, combat climate change or to manage the energy transition. More importantly, I think the industry can no longer afford to develop and maintain these very large monolithic code bases for their wave equation-based imaging and reservoir simulations. So they need to make a switch, and some of them are. I think this is important because also young people may not really be interested in working with these old impenetrable Fortran and C code bases. And by the way, this is not limited to only oil and gas. The national labs face similar challenges dealing with their HPC legacy codes. So I think there's a wonderful opportunity there as well.
Yeah, capture that excitement and improving things at the same time. And speaking of kind of what you're talking here, software, what is unique about the software framework that you all outline in this paper?
So I think the most important aspects are the use of abstractions and separation of concerns, right? I would say that. Also, the use of modern scalable software design, symbolic computation, and so on. Look, by exposing the underlying mathematical, statistical, and geophysical structure, rather than obfuscating it with performance-inspired programming clutter, we make it easier to implement relatively complicated but still performant algorithms. Something that is difficult to do, if not impossible, with these impenetrable optimized code bases most of us are still working with now. And I think this also explains why contractor companies and oil companies are struggling, for instance, to integrate machine learning into their wave equation based workflows. They're really struggling with it because they're faced with all these complexities.
Yeah, geophysics is complex enough. And you mentioned it in that last question and several times in your paper, this idea and the power of using high-level abstractions. What do you mean by that term?
So, the high level abstractions, we basically something where we try to tackle the fact that we cannot expect people to be experts in everything, right? And I see this with my students, right? For example, I cannot ask even the very stellar good students in Georgia Tech to code up a very sophisticated parallel algorithm in some low level language using some complicated parallel message passing interface, for instance. However, by using these high level abstractions, I can. And because of that, we have occasion after occasion where we see that my students can build these more complicated algorithms because these abstractions allow you to hide the complexity and handle separation of concerns. So you don't have to be bothered with some of these details that basically make it difficult to run this or develop these sort of codes. And I think this has already resulted in a bunch of novel approaches, and one we demonstrated in the paper, and that is ready to be validated at scale.
Speaking of the paper, going back to it, what excited you about the results of this study?
Well, I think started to say it's just an off-the-cuff idea of doing, say, end-to-end permeability inversion. So basically, you take many time-lapse surveys and you try to estimate the permeability. So you basically looking at the flow, and it makes sense to look at time-lapse surveys because flow is something that occurs over time, right? So, and that's really we made possible with this sort of abstracted approach. We were also able to swap out a socio-academic reservoir simulator for an industry strength one that's developed in Norway and that's made available as open source. And it includes sensitivities that you really need if you want to do inversion. And we basically got these early results in a matter of days rather than years. And, that is very difficult for industry to do. And they're struggling with that. And I think that stifles innovation.
Yeah, if you can close that time horizon, I mean, who knows what what successes can happen at that point. What remaining challenges are you most looking forward to working on that you started to address in this paper?
Well, so I think one of the things in academia is a bit difficult to do is to have access to compute. So for us, it's difficult to demo these things in 3D. The national labs and so on are not really set up for this. And also, what we're looking for is to help drive and accelerate innovations to help us navigate through the energy transition. And of course, to continue to train very young and versatile geophysicists at Georgia Tech.
Yeah, speaking of training young geophysicists, what are a few technologies, software libraries, or other similar resources that you think are essential for modern geophysicists to understand and use?
Well, there are many. And so there's also, there's a lot of activities, for instance, in the software underground, but I will limit myself to the ones that we looked at and used in the paper. And this is, by the way, a whole table of software we used. So we used two external code bases, DeVito, which is a just-in-time compiler for wave equation solves. And that's, by the way, running in production at several companies. And we have been major sponsors, have given a lot of input to that project. And then there's U-Tool, which is the tool to do, say, reservoir simulations. And then, of course, you have to sort of familiarize yourself to integrate all of these with modern techniques that are known as differentiable programming. They also undergird machine learning, so it allows you to take derivatives so you can actually optimize certain things, train, in other words. Now, of course, you need to also look at machine learning. So we integrate everything with machine learning. And keep in mind that we'll integrate that all with the classic physics-based methods and integrate those with machine learning. So you have all these things across the board. And the sort of the concepts we dealt with in the paper allow you to do that.
Yeah, that's a really helpful table you have in the paper that people will see all the resources you use. And you mentioned Software Underground. I'll add a link to that. That's a pretty important community to join if you're in this world for sure. How would the democratization of technology design do you see improve the oil and gas industry?
Well, I think the answer can be short. I mean, simply put, we cannot afford not to, right? So this is the only way forward to meet the challenges of the energy transition from my perspective. And to meet these challenges, we need exponential growth. And we see the opposite because of the complexity of these monolithic codes, right? These codes need exponential work, more and more efforts to gain very little in capability. And from my perspective, that's really a showstopper. And that's not what we need in these challenging times.
You and your co-authors took the step to allow this paper to be open access. Why was that important to you?
Well, I think we only need to look at the machine learning community, right? Where open access, so I'm talking now more about open access to software, right? So you have to only look at what happened in the 90s with Microsoft, right? Who dominated everything and they were big detractors of Linux. But then they made up their mind and actually joined the Linux Foundation. And you see it also with all these open source projects for machine learning tools that are pushed as open source. And that really accelerated innovation in that area. I think we could learn a lot from looking at that community.
Do you think that open access will have a role in the digitization of energy moving forward?
I think so. And it's also open access for publications, by the way. The reason I bought this open access is that I want our message goes to a much larger audience because the problems and the challenge we are trying to face are faced by others, as I alluded to earlier.
That's a nice you put your money where your heart is in talking about open access and open software by allowing anyone to read this article, which is incredible there. And what next steps would you like to pursue from this line of study?
Well, first of all, I think there's still only today a minority of companies that are embracing this new paradigm we've been talking about, right? So I would like to push more over, to make that decision to join this. And it's really a paradigm shift. There's just too many people still handwriting CUDA. So we need to work on getting more people on board. In the meantime, we will also look at the use of these latest developments in AI. For instance, we want to look at how to use large language models to translate legacy codes to abstractions and abstractions to code. So we can capture the knowledge that resides in these codes and the people who wrote it, but the people who wrote it are retiring. And so the companies are hemorrhaging a lot of knowledge, right? So we're trying to build a domain-specific language on steroids in a way. And we also envisage that the use of our abstractions, and that's really embodied in this symbolic domain-specific language, that we can use those to cross-validate the output of AI and to reduce hallucinations that these programs tend to create, because you have a structured approach to fact check, and that's the mathematics basically, right? And that all maybe allow us to reverse engineer some of these large code bases that now run the risk to go into oblivion because the people who wrote them are not there anymore.
Lastly, here, what principal teaching or experience has helped you succeed in your field?
Well, I can be short. You have to be stubborn, ignore old-fashioned ideas, So people, I remember they told me, oh, you have to teach your students to write MPIC programs. And I ignored that. And then they sort of turned their opinion because they saw how productive my group was by using more sophisticated tools. We would just be much faster than anybody else. But that needs visionary, right? So you have to be visionary and stick to your guns.
Yeah, we'll link your article, and as we've mentioned, you'll be able to read it no matter who you are, which is an amazing thing that you allowed for this paper. And I look forward, Felix, to seeing what else comes next in this line of research.
I enjoyed this conversation, and I hope it will appeal to a large audience.
You reached the end of Seismic Sound Off. Thank you for listening to this episode. If you want to be the first to know about the next episode, please follow or subscribe to the podcast wherever you listen to podcasts. Two of my favorites are Apple Podcasts and Spotify. If you have episode ideas, feedback for the show, or want to sponsor a future episode, visit seg.org/podcast and find the box titled Contact Seismic Sound Off. Zach Bridges created original music for this show. This episode was hosted, edited, and produced by me, Andrew Geary at Treasurement. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.